Everybody's joining, it looks like. Okay. Hi, everyone. Welcome to our second EGI webinar of the spring season. Today, we will be hearing from Dr. Pengzhu Xing, and he will be discussing thermal cooling effect of long-term circulation in enhanced geothermal systems, Raft River and FORGE. So after, there will be some time for questions. So you can either raise your hand at the end if you have a question, or you can put it in the chat box. Either one works. Looks like some people are still joining, so I'll admit them. Okay, and with that, I will hand it over to Dr. Xing.
Thank you, Jennifer. So, so today I will talk about the thermal cooling effect of long-term circulation in enhanced geothermal system. I will talk two cases, Raft River and Utah Forge. So, the map on the right shows the geothermal heat source in the United States, and so the temperature at 4 miles, 6 kilometers, it looks like this. So it's quite a huge amount of heat source we can explore for geothermal in US. There are two types of the geothermal resources. One is conventional hydrothermal. You have heat source, water, fluid permeability. So this just happen naturally. Another type is called enhanced geothermal system. So you have only the heat source, you only heat, but you lack of the water or you lack the permeability. So for the hydrothermal is a sweet spot. But it's very you have a very limited location. You have hydrothermal, but for EGS, um, unless your drilling and other techniques is mature, you can do it theoretical anywhere in the US or in the world. So here I talk about two types of enhanced geothermal system. So type 1 is based on the hot dry rock. The perfect example is Utah Forge. So it's in Milford, Utah. The only thing you have is the hot dry rock. So in Utah Forge, we drill a injection well, we do the stimulation, and we drill a production well. Then we'll circulate the waters through this create stimulated fraction network. But there's also another type of the EGS. So it's you have natural fractures. You can connect injector and the producer, but as times goes, this permeability or this performance of the injector may degrade. So then you need to do some enhancements to do some stimulation to increase performance. And this is the case for the Raft River EGS project. So here I'd love to briefly introduce the Raft River geothermal development. So the Raft River geothermal field is 100 miles northwest Salt Lake City, is on the border of Utah-Idaho border. The site was originally developed from 1974 to 1982 by the U.S. Energy Research and Development Administration, and later the U.S. DOE. And then this site this was acquired by U.S. Geothermal in 2002. And then the 10 megawatts of the plant came on stream in 2008. And in 2012, the Raft River geothermal field was chosen by the DOE for an EGS demonstration project. So what we do for the EGS project in the Raft River? So look at this red dash line. there's a original well is RG9, but this well is some commercial well. It means like this its injectivity is not very good. So then, under this EGS program in 2012, another well, RG-9 ST1, was drilled at same drill pad. But then after drilled well from 12 and 2014, three hydraulic stimulation was conducted as 12 of these as new well RG-9 ST1. Then there's the long-term cold water injection. So the data show that following the hydraulic stimulations, the injectivity increased, and it's continuing to increase with a cold water injection. So here's some geologic information of this RG9ST1. So there's a fracture zone as around 5,650 feet from we can see from this image log, and also we can see the temperature. For the temperature is lower as this region. So this region is where the fluid goes. So then we do hydraulic stimulation. So here's a table shows the three hydraulic stimulation. So it spanned quite a long time, but so the first one is right after drilling the well. So it drilled it's with a lower pumping rate and lower volume injected. And the second one is about more than 1 year later. It's do 1 month long stimulation with lower pumping rate and also a lower pressure. So then there's third one in 2014. So this one with large pumping rate, and also the injected volume is also much larger. It's larger in the hydraulic stimulation 1, but it's lower than the hydraulic stimulation 2. So some studies indicated that for hydraulic stimulation 1, 3, there's a hydraulic fracture propagation that's create new fractures. In the hydraulic stimulation 2, because the pressure and the injection rate is low, it's mainly hydroshearing. So then we look at some data here. So the injectivity. So the injectivity means the injection rate over the injection pressure. So the top one shows the pressure and also the injection rate change with time, and the bottom is the injectivity. So and we can see that during the hydraulic stimulation 2, the 1 month long injection hydraulic stimulation, we can see the injectivity gradually increase. But after the hydraulic stimulation 2, this injectivity is pretty steady. It's not increased too much. But then we do the hydraulic stimulation 3 is with higher volume, higher rate, with a higher rate and higher pressure. And amazingly, that after this hydraulic stimulation 3, the injectivity keep increasing until like 2 years is increased about 2 years, more than 2 years. So and we also here's some microseismic events. So the white one, the white dots here is the events occurring during the hydraulic stimulation 3, and this pink one is the events occurring after the hydraulic stimulation 3. It means after hydraulic stimulation 3, this this microseismic unit is expanding a lot, So, but it stopped expanding after the November 6, 2014. So, and the azimuth of this pink one is a north 60 degree east, and it's consistent with the orientation of the narrow Downs fault in the Raft River area. And the white one is the microseismic class that's during the estimation 3 is consistent with the fracture region, the fracture zone, the orientation fracture in the image log. So the question is why so the injectivity keep increasing after hydroxylation 3, and also it's also increased even after these hide this. So yeah, anyway, so there's the even after these expanding of microseismic clouds is also keep increasing. It's keep increasing, and so the focus of this study is that we focus on that why. So imagine that after there's hydroxylation 3 is with higher injection rate and high pressure, it can overcome some pinch point uh, in this fracture network. So then it can so this indicated by this microseismic cloud, this means this fracture is propagating, but at some point it stopped propagating. But still you have this injected increase. So how to explain that even after the microseismic clouds stop expanding, why the injected increase? So the hypothesis is that it's due to the thermal elasticity. So so the basic theory that you keep circulating cold water, so you result in progressive cooling of the reservoir, and the cooling of the reservoir leading to the increase in the fracture aperture, and then it's an injected increase. So the methodologies, so we use the 1D approximate solution to estimate the injector aperture change due to thermal cooling. So this can give us the first order of the solution. And then after that, we do a detailed fully coupled thermal hydromechanical modeling and to simulate the circulation in Raft River. So here's look at this figure. So it's one injection well, one production well. So they're connected with a fracture network. But here is simplified as a single fracture, So the relationship between the fracture, the injected and fracture aperture can be approximated as a cubic law. So you have a larger aperture, then your injectivity is like in order of power 3 increasing. So it's quite a lot. So then this aperture change can be related to the evolving thermal stress. So it's related to the alpha is a linear thermal expansion coefficient. So and the temperature change, and also the D is the penetration depths like perpendicular to the fracture surface. So in this direction, and can be expressed as this related to the Schrock thermal properties and the time. So then we can the aperture then can be given as like this. So there's a square root of so the aperture change with the square root of time. Okay, so then we do two things. First, we can make some assumption of these parameters. Uh, uh, about linear coefficient, thermal expansion coefficient, the thermal properties. It should be in the ballpark. It's not cannot be too far away. And you make assumption of these parameters. Then you can calculate these coefficient. So the coefficient is calculated as like 7 uh, 10 power of -7 meter per second square root. Okay, so then we come back to the data. So from Raft River, we can have this kind of plot from the data in the field, and then we can put the linear line here, and we can get this coefficient. So we compare them. Of course, they are not exactly matched, but I think it's reasonable because given the assumption of these the temperature change over in the equations, so the temperature change in the 1D equation, the temperature change over the entire diffusion length is the same, but actually it's not. So I'll show you in the fully 3D model. And also the uncertainty is assumed parameters, but only through this 1D approximate solution, we can see that this thermal cooling effect can explain why this aperture change and also the injectivity increase during circulation. So then we do a 3D modeling of these to simulate the for injection in Raft River after stimulation. So the domain is 3,000 by 2,000 meter, and also there's one single large fractures represent the complex fracture network. This fracture length is 2,800 meters. It is consistent with the microseismicity events cloud I showed earlier, and the height is 250 meters. Also, it's roughly the height of the microseismic cloud. And so there's the water will inject through the inlet, and it goes through the long fractures, and it's come out through this outlet. So the outlet, there's a pressure boundary there, the pressure. So this is a sink. And we'll also apply a thermal gradient of along the vertical direction. It's some parameters I use in the modeling. The injection. So the temperature, the initial rock temperature is about 150 C. The inject water temperature 50 C is from the data. And the simulation time is about 9 months, 272 days. So here's how the modeling works. We use Tasca's Xi to calculate this. So first it will calculate heat transfer, and the temperature change will result some the thermal stress, and also the aperture change. And the aperture change will affect your fluid flow. So they will have some pressure change if you have aperture change. So then after that, you do some iteration to get a quality state of mechanical equilibrium and a quality state of fluid flow field. Then you have a new fluid flow velocity, and you go back to run the next time interval until the end of this simulation. So here's the numerical simulation results. This is fracture aperture change. And so as I said, so this fracture aperture is not uniform. It will change with time. And so if you look this state, so this state is at its end of this simulation, and we also have some history. So the change with time for these curves. But if you look at these end state of this circulation, we can see that this aperture at close to the injection point is much larger than the away from this injection point. But initially they are all the same. But with time goes, the aperture change, the increased increased close to the injection point. And and we know that this the maximum aperture is not as inlet. It's so the red point has some distance to the inlet. So the inlet is at the very edge of this at the edge of this fracture, but the maximum point, maximum aperture is not same as the inlet. So and if we if you look at the aperture in the inlet, it's increased a lot at the beginning, but then it slowed down after 46 days. But we are not just looking at the inlet. We can look at the average of this aperture if to so they are increasing. Yeah, they're increasing. So yes, so the maximum, even the inlet is not always increasing, but the maximum aperture is always increasing due to the thermal cooling effect. So here is a pressure. So if you look at the pressure at the inlet, it's keep decreasing. So please note, so this is consistent to our field data, right? So the injectivity is keep increasing because the pressure is decreasing, so the injectivity is increasing. So because here we keep the pumping rate constant. So this plot show the fluid temperature and also the fluid temperature history. So the fluid temperature has only decreased by 3 degrees C at 116 days and become relative constantly afterwards. And so this is show the rock temperature at end of this at end of 9 months injection, and also this temperature history. So we can see that this is so this is a vertical direction, and this is a horizontal direction, and so we cut the fracture plane. So there's a fracture here. As we can see that the rock the temperature around the rock surface, the rock temperature around the fracture surface is decreasing as due to the cold water injection. Okay, so here, this plot show that the injectivity change with time, and from both the simulation results and the field change. So this blue line is show the simulation results, and this red line shows the field inject change. So overall, the trend is similar. So your injectivity increase relatively fast and then become relatively flat at the end. So similar here. So they do not have exact match, but I think the trend, but they are very close. See that the injected change in our simulation is about 1.7 10 power -8. and the field is 2.5. I treat it as a very close match. And here's the aperture. So this red line is maximum aperture change, and it's always increasing. And this is the blue line is aperture change as an inlet, and the black line is we estimate aperture change in the field. So the simulated maximum aperture increased by 1.9 millimeter after 260 after 260 days of the cold water injection, and the inlet increased by 0.64. So the numerical forecast trend of the maximum aperture increase matched the change interpreted from the 1D solution, and the aperture increase simulated from the operating solution is smaller than the simulated inlet aperture increase. That's because for the 1D, so remember there's this, we cannot measure aperture change in the field. It's just the estimate for 1D solution. So this 1D solution is have a single a single value of the aperture, but the numerical in the numerical model is we can, as I showed earlier, so the aperture is varying from the inlet to the outlet. So conclusion that the injected increase with circulation time in the well RG9-ST1 at Raft River, it can be explained by the effect of thermal cooling. And we use 1D a carbon solution to estimate injectivity change in the cooling, and the inferred fracture aperture follow linear trend supporting the hypothesis cooling was a dominant factor of the injectivity improvement. And then we conducted 3D fully coupled modeling, simulated long-term circulation, not only trained of the injectivity match with data, also the magnitude of the injectivity increase approximately match the field data. So we conclude that the thermal cooling effect results in thermoelastic stress and aperture change could be a major reason for injected increase in an injector. It doesn't mean that there's no other effects. So, but this, so in study, I just want to say that the thermal cooling could be can explain that for why the injection increase for modeling for yeah. So then so we have this conclusion. So the cold water injection could serve as a massive increase injectivity during long-term circulation. Okay, so next I will talk about Utah Forge. We also do some work circulation in the Utah Forge. So first, I want to briefly have an introduction with on the Utah Forge. So Utah Forge is located in the Milford, Utah, so far from Salt Lake City. So I think it's till now like five or six deep wells are drilled on site. And here I want to brief you about the field operations at Forge. So in 2020, we drilled the injection well. Then in April 2022, we conducted 3 stages of stimulation at 16A. And in 2023, we drilled the production well 16B. And right after the drill, the production well conducts initial circulation test. And in last year, in April 2024, conducted commercial scale stimulation with propellant. And right after that, we conducted the 9-hour circulation test. And 4 months later, we conducted a 1-month circulation test. So this is some results from the 1-month circulation test. So it's from August to September 2024, between 16 and 16 B. So uh, the so the blue line is efficiency. So we inject with 10 barrel per minute. So the injection, the efficiency is the water coming out from 16B is keep increasing. Leading to a production rate of 9 barrel per minute and with wellhead pressure of 65 degree F. So if you look at this injection, the data from the injection side, so the blue line is a wellhead pressure, and the orange line is the injection rate. So the injection rate is constant after April 10, sometime that. So the pressure increased a little bit until like April 18. And then after that, we can see that there's a 200 psi pressure decreasing with a constant pressure with constant pumping rate. So also this 200 psi pressure decreasing can also be explained by the thermal cooling effect. Again, I want to mention that it's not the thermal cooling effect maybe not only reason to without this pressure decreasing, but it is one of the reason at least it can be explained what happens on field. So again, so you if you put some numbers here, use this cubic law approximation. So I assume like the fresh height is 300 meter, fresh length is 300 meters, and the injection rate is because because a lot of there's 10 stage of hydraulic estimation between A and B. Here, look at only one stage, so the injection rate is divided 10 barrel per minute by 10 stage, so the injection rate is only 0.77 barrel per minute in one stage. And the initial injection pressure, and you have 200 psi pressure reduction. And if assume the initial aperture is 0.18 millimeter, then you calculate you can get the final aperture. If you have 200 psi decreasing, the final aperture is 0.21 millimeter. So this 0.18 millimeter is roughly the size of the proppant we used during stimulation. So after this 1 month circulation, you can you can have a 0.03 millimeter aperture increase. So it's 0.03 millimeter increase, maybe not big, but you remember that it's a cubic law, so it still can have without 200 psi pressure decrease. So the conclusion that the injectivity increase with continuous cold water injection circulation for Raft River and the FORGE, and this injectivity increase can be explained by thermal cooling effect. And here's some references. Thank you for your time. So I'm happy to answer any questions.
Pingju, it looks like Herman Levitt has a question in the chat box. Are you able to see his?
Okay, have you looked at the enthalpy when injecting cold water? Uh, uh, no, I haven't looked at the enthalpy. Uh, so no. So if you can speak out, you can elaborate your question. So
Yeah, I can. Sorry. Hey, thank you very much for this wonderful presentation. It was very helpful. A lot of great information in it. And my thought was basically, hey, you have the temperature, you have the flow rate. And so when you cool down the system in a certain way, so you have the input, you have the output. So you could actually check on the efficient enthalpy. So what is the impact when you cool it down? Because you cool the whole system down in a way which is actually have these thermoelastic reactions, which is, I think, a very interesting aspect. So
You mentioned the temperature production temperature in the Raft River, right?
yeah.
So so we have because all these things are mixed. So if you look at this figure, so these blue ones are the injection well, and these red ones the production well. So
Mhm.
you inject it through here, and all mingle together to the power plant. So it's hard to tell what's the production temperature from this well. So
Okay.
and we don't have that data.
Oh, you
So,
don't have the.
but from the power plant side,
Mhm.
I think Gilmore told me that the temperature, the production temperature in the power plant is relatively stable. Uh, yeah, for these years from like 2013 to I think what's the date? Yeah, to 2019. So the production temperature in the power plant is quite stable.
Okay. So you have
Yeah.
a commingled fluid at the end of the day. All right. Thank you very much.
Any other questions? Can raise a hand so Jennifer can bring to the stage.
Looks like we got one in
Right.
the chat box.
Yeah, can you comment on source aperture value for the fuel forge? Yeah, so so here I just assume the initial aperture is 0.18 millimeter. So I think we use the 100 two propellant, one is 100 mesh, another 70 mesh. I think you calculate if it's a single layer propellant, I think this is the 0.1 millimeter is the size of the sand. Uh, and then, so you plug this number in, and because you have 200 psi reduction, so you can calculate a new final aperture, this 0.21 millimeter. So, yeah, that's how I get this number. So again, so this is for the single fracture. There's a lot of fractures, but issue will be similar. So this fracture height and length is from the I think I look for the stage 3. So um, yeah, the change. Again, yeah, this cannot be 2 millimeter because if you have a 2 millimeter initial aperture, your pressure cannot be 2000 psi. So in the Raft River case, I assume a 3 millimeter initial aperture because the pressure here is pretty low. So you see the pressure here like is only 200 psi. Then you can assume like a 2 millimeter aperture. But in Forge, we have like 2000 psi, 3000 psi pressure. So you just cannot assume like it has a 2 millimeter initial aperture. Yeah, but it's a good question, Chris. Yeah. Also, I want to comment that on this calculation, I also consider the friction. So, for the injection, this wellhead pressure, so it's not exactly what's inside the fracture, but I already consider the friction during this calculation. Yeah. Yeah, there's another question from Nicholas. So yeah, there will be longer circuit test planned in this September or later. So we'll do like uh, at least 3 months circulation between 16 and 16B. Yeah, so I'm not trying to modeling these uh, yeah, a lot of people are modeling these to kind of match this history match the pressure and also the temperature for this 1 month circulation. Um, uh, and I also have done some modeling as a good match within 1 month. Uh, yeah, but since they're challenged because since the temperature change, since the aperture change is so little, it's posed some challenge on the modeling. Not like Raft River. So Raft River because your initial aperture is like in order of millimeters, so it's relatively easier to model this. Uh, so right now my model does not consider in 1 month. So my 3D model does not consider the thermal stress, cooling effect, temperature change. But if you run long time, the circulation is like in years, you have to consider that change, temperature change in the model. Yeah. This is another question from Wen Cheng. Are you planning to incorporate DFM with the model simulated fluid circulation? Uh, yes. So for the Raft River case, I oversimplified with one large fracture. Uh, but for the forge modeling, I do not show here, but I consider DFM in the modeling to do the to simulate the fluid circulation. And so what is the expectation in terms of results? So as I just talked, in the long term, if you circulate like years in 1 year, 2 year, this thermal cooling effect cannot be neglected. You have to consider that. So question from Muhammad. Um, you also similar system efficiency, breakthrough cooling. No. So, is this a good question? But if you look at the Raft River case, so you have very permeable uh, fault. So, most of the fluid will circulate through that fault. The fluid loss, there could be some fluid loss, but that's fluid loss is uh, compared to the you imagine you have a very large channel, so most fluid will go through the channel, and will be lost to the um, to the reservoir, um, and also the permeability across the fault is very small, very small. And for the case of forge, you see the efficiency. It because during the stimulation, you create a lot of you stimulate large reservoir. So your efficiency increase as you keep circulating, and at end, is your efficiency is 90%. So only is 10% alluding to the uh, to the pores of the reservoir. So yes, you can simulate that. You can have dual permeability porosity uh, model. So, but as time goes, because uh, in the case of for Forge, like because the initial permeability of the rock is so low, so I think uh, I imagine if you have keep circulating, the efficiency will be even greater than 90%. So for the long-term effect, I think for your competition efficiency, I think you can neglect the porosity of the matrix. But for the shorter term, like yeah, this does affect your efficiency. So, in Ford Track, do you have an estimation of how much of the back production of the injected fluid? Yeah, so yeah. So you look at figures, so this blue line's efficiency means how much percentage of the fluid is coming out. So the 90% means if you inject 10 barrel per minute, then 9 barrel per minute are in the production well. So yeah, because at Forge is initially you don't have any uh, natural permeability. It's quite tight. It's quite tight. Then after you do some stimulation, you create some fractures. Then so because at start of this circulation, you need to recharge of this fracture system you created. So, but after you recharge, then it's can be 90%. And I imagine it could continue to increase even you can be greater than 90% after you fully charge your reservoir, and it won't lose too much fluid because you don't have any natural permeability.
Hey, uh,
Uh,
last chance for any more questions?
oh, okay. Did you consider current embedment in the aperture size? No, I did not. So yeah, so it's also a good topic. So it's how the propellant packed in the fracture. So in my calculation, or in my modeling, the initial aperture I assume is just a single layer, but it can be other things. Um, Also, from the for the long-term case, your propellant will be dissolved in the high temperature environment because your propellant it's just thin, right? It's coarse. So as time goes, the propellant can be degraded. It can be harmful. So yeah. Efficiency if the test was conducted at cooler temperatures. Uh, I don't know if you're talking about the Raft River. The Raft River, we just do not know too much about the production side because it's all mixed together to other wells. But for the Forge, um, So the water we use as a circulation is pretty cold. I think is during this 1 month circulation, it's open. So we just we get water from the water well, and it's just ambient temperature. I think it's it's about 27, 28 degrees C. It's water very cold. So uh, I yeah, it's difficult to thinking about the temperature of the rock mass. Uh, you mean the efficiency of the heat extraction? Yeah, I think yeah, it's the cold water you have higher efficiency because the temperature difference is bigger. So then your efficiency will be larger if you use more cold water. That's true. Yeah. Another question is, do you see any sign property dissolution in the marrow signal? Uh, um, uh, yeah, I don't know. I don't know. So we have geochemistry in our team, but I don't know if he's here or not. But I don't know this answer. The answer to this question. Additional fracture aperture increase in initial. Can we expect any initial or long-term extension of the hydrofraction angle due to thermal induced fractures? Yeah, so yeah, it could be it could be some very slowly uh, uh, extension of this fractional network due to the thermal cooling effect. And also Raft River is a good example because after stimulation 3, you see these microseismics, the pink, is all after you do the stimulation. So and it's expanding a lot. So I think yeah, there's some mechanisms like when you keep injecting, your network can expanding, but this cannot expand forever, right? So for the Raft River case, at some point it just stopped. Yeah, I don't know why, but uh, it stopped in 1 year later, and but your pressure, but your injected keep increasing even after these uh, microseismic clusters stop expanding. There's definitely some effect of this affection network in Raft River. In the Forge, we're not sure because we don't have like long-term data.
Okay, Pengzhu, should we wrap up?
Yeah. Thank you very much. Thank you for your time. Thanks for attending.
Thank you, everyone, and go to our website to find out when the next webinar is. Okay, thank you for listening.